Hi, welcome. My name is Or Keret, and in this seminar I will talk about the paper Testing Juntas Newly Optimally by Eric Blythe from Carnegie Mellon University. Let's begin. Table of contents. So, as per usual, let's begin with some motivation. Our main definition will be k-juntas. A function on n variables will be called k-junta if it depends on at most k of its variables. This might be interesting because testing whether a function is k-junta could prove to be useful in data science applications and other scientific fields. Let's say, for example, we're trying to model a function that is a k-junta, meaning it depends only at most k of its variables. Then, we could select only about k of the most dominant features and use them exclusively. This way, we can select only a small number of features and still model the function in a pretty good way. This feature selection process could help reduce overfitting and other problems we might encounter when trying to model complex functions. Our main tool will be a k-junta tester. It will test whether a function is k-junta or if it is epsilon far from being a k-junta for some approximation parameter epsilon. If the function is a k-junta, then feature selection for k features will work pretty well. If it is epsilon far from being k-junta, the feature selection probably will not work, will not get us good results. Okay, so we have k-junta testers. They get a function and they determine if it is a k-junta or if it is far from being a k-junta, and we will measure their efficiency by the number of queries they make to the function. So before this paper was published, the best k-junta tester that was known had used soft O of k raised to 1.5 all that over epsilon queries. That was the best number of queries, the minimal number of queries we had the k-junta tester for. And another bound was shown before this paper was a lower bound on the number of queries for a k-junta tester. It was big omega of k. So what was basically known that the best k-junta testers will use a number of queries between big omega of k and this upper bound. So the research presented in the paper this seminar is based on, was motivated by the desire to close the gap between this upper bound and lower bound. And it really does this successfully by presenting an algorithm that makes only big O of k over epsilon plus k log k queries to the function, which is really close to be optimal. It's really close to the lower bound. It's optimal up to a logarithmic factor because here we have k and here we have k log k. And this k over epsilon, it disappears when we set the approximation parameter epsilon to be constant. So this result is really optimal. It's very close to the lower bound, up to a logarithmic factor. Let's move on to the preliminary section. Let's describe the setting of the paper. So we're talking about functions f from set x to set y, where both of these sets are finite. The set x is actually a product of some n sets x1 to xn. This function should be a multivariable function because we're interested to check if this function is dependent only on a small number of its variables. So this function is multivariable. We will assume we have some probability space omega defined over the inputs x. So for example, if we're talking about classifying patients in some machine learning task, this can be thought of as the patient's data. And an assumption we will make about omega is that it is a product probability space, meaning that each coordinate will be independent of the other ones. So for example, if we have the height of the patient and the weight of the patient, we will assume that these values, these random variables, are independent. So we will use this assumption in our proof. Other notions we will use are xs and xs ys s bar. So for every subset s of the coordinates, we will denote by x subscript s the values of x taken in the s coordinates, and we will denote by x subscript s y subscript s bar the hybrid vector obtained by taking x in the s coordinates and taking y in the s bar coordinates. We will also denote by I a random partition of the n coordinates into s disjoint sets, and in this paper this partition will always be obtained by assigning each coordinate to a uniformly chosen set from the partition, and all these samplings will also be independent for each coordinate. We'll now make some definitions. We'll begin by defining influence. So the influence of a set of coordinates S in the function f under our probability distribution omega will be the probability that the function gives different values for these two inputs, where this is a hybrid input. And this definition is intuitive because these two inputs agree on the coordinates s bar and might disagree on the coordinates s. So this is the influence of s in the function f. And if for some set of coordinates s we have an influence that is bigger than 0, we will say that s is relevant for f. F is dependent on the coordinates in s. And now we can define juntas. F is a k-junta if it has at most k relevant coordinates, where here coordinate is just a singleton, a set of size 1 with a single coordinate, and then we can use the definition of relevant with influence bigger than 0. And conversely, f is epsilon far from being a k-junta under our probability distribution omega if for every function g that is k-junta, the probability for some x that they disagree on this input x is bigger than epsilon, then f will be, we will say that f is epsilon far from being a k-junta. Let's see proposition 2.3. So if f is a function that is epsilon far from being a k-junta, then for every subset of the coordinates j that has cardinality constraint k, the influence of all the coordinates but the coordinates in j is at least epsilon. This proposition will be useful to us later, and we will also prove it later, but for now let's continue. As it turns out, looking at coordinates in groups instead of individually can be useful to us. So we will define partition juntas, which will be similar to juntas, but in the context of partitioning the n coordinates into groups. So let I be a partition of the n coordinates. We will say that f is a k-part junta with respect to the partition I, if the relevant coordinates in f are all contained in at most k parts of I. So if we take all the relevant coordinates of f, there should be some at most k parts of I where all these coordinates are located. And conversely, we will say that f is epsilon far from being a k part junta with respect to the partition I under our probability distribution omega, if for every set j formed by taking the union of at most k parts or k parts, it's without loss of generality, in this partition, then the influence of all the coordinates but the coordinates in j is at least epsilon. This definition is similar to proposition 2.3, but in this case it's not a proposition, it's just by definition. And so this is the definition of partition juntas. Let's now define junta testers. So their definition comes from the more general context of property testing. So a randomized algorithm A that queries a function on a small number of inputs is an epsilon tester for k juntas under the probability distribution omega if it accepts k juntas with probability at least 2/3 and rejects functions that are epsilon far from being k juntas under omega with probability also at least 2/3. The query complexity of A is the number of queries it makes to the function before accepting or rejecting it. And we will say that if a junta tester accepts juntas with probability 1, then it has one-sided error, like in the case of the algorithm presented in our paper. Let's also note that this algorithm has some gap. For functions that are k juntas, it should, with high probability, or in our case, with probability 1, output yes, and for functions that are epsilon far from being k juntas, it should output no with high probability, but for functions that are neither epsilon far from being k juntas and neither k juntas, we have no guarantee. So this junta tester has some gap. It has a range of inputs where we have no guarantee about the output. Let's see more setting details that we will use to analyze functions. So let's denote by R superscript y the vector space generated by the set of all formal linear combinations of elements in Y. So what are formal linear combinations for an arbitrary finite set Y? So they can be just thought of as taking elements of Y, multiplying them by real coefficients, and then summing everything up. But Y is an arbitrary set, so this sum doesn't need to have any real meaning. Y can be even a set of animals or any other abstract set of objects, and we can just write this expression down, and the result of summing or multiplying here doesn't need to have any real meaning. So we just write this sum and call it a formal linear combination, and then we can treat this as a vector defined by the coefficients of the elements. So here the vector will be 1/2. This will be the first element, then the second element will be 0.72, and then 5.3, and then these vectors define a vector space that we will denote by R superscript Y. And then we can also define inner product between these vectors. So if we have one such vector V and another vector W, their inner product will also be defined naturally by taking the coefficients of the corresponding Y's, multiplying them together, and then summing up all the coefficients, and this will give us a real number. Now, let's take all functions from X to the vector space of formal linear combinations, and let's form an inner product space under the following inner product. So for F and G, which are functions of this form, we will define the inner product as taking the expectation over a random sample X from our probability distribution, and then just taking the expectation on the inner product of the values that the function is given X. Then we can naturally define the L2 norm of a function from this inner product space to be the square root of the inner product of the function with itself. Then let's define pure valued functions, or just denote pure valued functions to be functions from X to Y. Then we can take these type of functions and think of them like functions from X to the vector space of formal linear combinations, where the corresponding vector to Y is just 0, is the coefficient 0 for all elements that are not the right Y, and 1 only for the element that is the correct Y. And then we can immediately see that the L2 norm of such functions is 1, because if we take the inner product of this function with itself, then for every input X, we will always get 1 for the correct output of the function, and 0 for all the invalid outputs. So we will just multiply 0 by itself many times, and multiply 1 by itself one time, sum everything up, so we'll just get 1. So all in all, this inner product will be 1, and the L2 norm of pure valued functions is 1, and we will actually use this identity many times in the next few slides. Let's now see an important tool we will use a lot called the F-Einstein decomposition. So for every function from our inner product space, it has a unique decomposition of the form f of x equals the sum of fsx, where s are all sets of coordinates. And this decomposition obviously needs to have some properties, so we will require that for every s subset of coordinates, another subset of coordinates s tag such that s has some element that is not in s tag, and for every y in x, we will first require that fs depends only on the coordinates in S, or equivalently, that the relevant coordinates of fs are all contained in S. And secondly, we will require that when we take the expectation over a random x of fsx and condition x to be equal to y on the coordinates of S tag, then this conditional expectation should be equal to 0. This second requirement can be intuitively thought of as when we take an expectation and we fix all the coordinates of x except at least one coordinate that we will leave unfixed, because S should have an element that is not in S bar. So even if we fix all the elements of X but 1, then if we take this conditional expectation, it will be 0. So as long as there is a variance in even one of the variables that Fs depends on, then if we take the expectation, the expected value will be 0. So this is the intuition behind this second requirement. And this tool will actually be very useful to us. An important property of the F1 decomposition is that it is orthogonal. So if we take two functions from the decomposition of F, which are different, so we require that S is not equal to T, then their inner product is 0. Then, because of this orthogonality, we also get Parseval's identity, which is a generalization of Pythagorean theorem for functions, or we can think about it like it's similar to Pythagorean theorem, but for functions. So for every function from our inner product space, if we take the sum of squared norms of the functions we get from the F1 decomposition, we can instead just take the squared norm of the function itself, and these two will be equal. And recall that we saw that the norm of a pure valued function is 1, so we also get that this sum is equal to 1, because the L2 norm of a pure valued function is 1, so we also get this identity, and we will actually use this identity a lot as well in our proofs. Now we'll have some propositions and corollaries, and we'll prove each one of them. So let's begin with proposition 2.9. For any pure valued function f and every set of coordinates s, the influence of s in f is equal to this sum of some squared norms of functions that come from the F1 decomposition of f. Let's prove this proposition. We'll begin by noting that the indicator of the event that f of x equals f of y is equal to the inner product between f of x and f of y. This is because f is a pure valued function. So f of x is just the formal linear combination that we have 1 as the coefficient only for f of x, and here we have 1 only as the coefficient for f of y. So multiplying these two vectors, we will get 1 if f of x equals f of y, otherwise we will get 0. This is just by the definition of inner product that we've seen before. So we can see that this indicator is equal to this inner product. Now we have this influence. By definition, it's equal to this probability, as we've seen before. Now, instead of taking this probability, let's take the complementary event, 1 minus the probability that these two values are indeed equal. But instead of taking the probability on the events that are equal, we can take the expectation on the indicator that they're equal. But instead of taking the indicator, we can take the expectation on the inner product. So finally, we get 1 minus the expectation on this inner product. So now that we have this expression, we can move on. So we have this expectation of the inner product. So we have f of x and f of this hybrid input. So we can instead look at the F1 decomposition of these activations of f. So this is just the F1 decomposition. And then we can use linearity in the first element of the inner product. And we also have linearity in the second element because this inner product is symmetric. So we can take these sums out of the inner product and then also out of the expectation because we have a linearity of expectation. So we just took the sums out. Now we have the expectation of this inner product. It is similar to the inner product we had before, but now we have t and u. So it's the functions from the F1 decomposition. So let's take this expression and divide the expectations into two distinct expectations taken on x and taken on y. X and y are taken independently from omega, so this is okay. Now let's push this inner expectation on y into the second element. It's legitimate because we have linearity in the second element of the inner product, like I've mentioned before, and because of linearity in the expectation, and because this first element isn't dependent on y. Now we have this expression. So let's take this expectation and switch it up with this conditional expectation. This is valid because here we have x taken on the s bar coordinates and y taken on the s coordinates, and here we just take y but condition it to be equal to x on the s bar coordinates. So this transition is valid. It's also valid because let's remember that this probability space is a product probability space, so we have independence on the different coordinates. So if we condition y to be equal on x and the s bar coordinates, or if we don't condition it, it doesn't matter. So now we have this expression. So we first saw that this influence equals this expression. Then we saw that this expectation equals this sum. So let's just take this expression. Then we saw that the expectation where we take on x and y is equal to this expectation where we first take on x and only inside take on y. So let's again take this expression and continue from here. Now let's explain this equation. So we have this expectation of fu on y, conditioned that y takes the same values on as x on the s bar coordinates. So if u is contained in s bar, that means we fix all the coordinates in u to be the same values as x. And because of F-Einstein definition, we know that fu relies only on coordinates in u. So if we fix all these coordinates to be values from x, then fuy must be equals to fux. So if we fix all the coordinates in u to be values from x, then fuy will be equal to fux. That's the first part. Otherwise, it means that there is some coordinate in u that is not fixed to be a value from x. And in this case, because of F-Einstein decomposition, this means that this expectation will be 0, because there is some coordinates that the function depends on, some coordinate in u that is not fixed in the expectation, and then from the definition of F-Einstein decomposition, the expectation must be 0. So earlier we saw that the influence is equal to this expression, but now we know that the only relevant u are u's that are contained in S bar, otherwise this expression is just 0. So let's just take the sum on T that is still a subset of n elements, but now u, we will only take u that are contained in S bar because these are only the relevant elements that are non-zero. And then we can say that this expectation is equal to fux, like we saw in the previous slide. And then this expectation on this inner product, this is just the definition of inner product between two functions. So we can just switch this up. So this is the sum from last slide. It is known that the F-Einstein decomposition is orthogonal, so there is no point in taking the inner product of two functions that are different. So we can restrict ourselves to the smaller set, S bar, and just take the inner product of the same function each time, ft, where t is in S bar, and take only this sum. Otherwise, if these two functions were different, it would be 0 because the decomposition is orthogonal. And then the inner product between a function and itself is just its squared norm. So we can just switch this up with the squared norm. So again, we have the influence. We have shown that it is equal to this expression, and that this sum of inner products is equal to this sum of squared norms. So now we have this expression. Because of Parseval's theorem and the fact that f is pure valued, we know that this sum is equal to 1. So now we've got this expression. Here we have all subsets of some coordinates. And here we have all subsets that are completely outside of S. So if we take all subsets of coordinates and subtract all subsets that are completely outside of S, or that have no intersection with S, what we've got left are all the subsets that have some intersection with S. So that's the sum we have left in hand. And this sum of square norms is exactly what we wanted from the proposition. So with that, we finish the proof of this proposition. This is the proposition that we just proved. Let us now see this corollary that says that the influence upholds monotonicity and subadditivity. It upholds monotonicity because if we will enlarge S, that means that in this sum there will be only more sets that will intersect with S because we've just enlarged S. So there will be more elements. So the sum can only grow, which means the influence will also grow. Of course, that is because all elements here are positive because we have squares. And influence also upholds subadditivity, because if we will take the corresponding sum to this influence, then every set that intersects S union T must intersect either with S or either with T. So every element in the sum that will appear here must appear either in this sum or in this sum that are corresponding to these influences. So generally we have that this influence will be smaller than the sum of these two influences. Now that we proved the previous proposition, we can define low-order influence in a similar fashion. It will be almost the same equation as we saw in the previous proposition, but here we will restrict the intersecting sets to be of cardinality smaller or equal to k. Now we'll have a new proposition that says that for any pure-valued function f and every k smaller or equal to n, the sum of the low-order influences of individual coordinates must be smaller or equal to k. Then, from this proposition, we'll gain another corollary that says that for k smaller or equal to n and theta bigger than 0, the number of coordinates that have low-order influence bigger than theta must be smaller than k over theta. That is because otherwise, the sum of individual low-order influences must be bigger than k, because we have at least k over theta individual influences of over theta, so this sum will surely be bigger than theta multiplied by k over theta, which is bigger than k, and that contradicts this proposition. And so basically that proves that this corollary is true, because otherwise this influence will be bigger than k. Let's now prove the previous proposition. So we have the sum of individual coordinates low-order influences. So let's open up the definition of low-order influence. So we have this sum. And now let's change the order of summation. We'll first take all sets of cardinality smaller than k, and only then take coordinates from the n coordinates such that these coordinates are inside these sets, and only then do the summation. And then because of the cardinality constraint on the sets, the maximal amount of coordinates that can be inside those sets is k, so we can just put an upper bound and take out k here. And we will also increase this summation. Instead of taking just sets of constrained cardinality, we'll take all sets. And now here, this expression, this sum is equal to 1 because f is pure valued and because of partial values theorem. So this is equal to 1, so all this expression is equal to k. So we have that this sum of influences is smaller or equal to k, and this proves the proposition. So now for the final proposition of the preliminary section. If f is pure valued and it is epsilon far from being a k-junta, meaning that for every k-junta function, the probability that f and this k-junta function disagree on an input sampled randomly from the input space is at least epsilon. Then for every set j of coordinates that has cardinality constraint k, the influence of all the coordinates but the coordinates in j is at least epsilon. So let's prove this proposition. We'll begin by defining an auxiliary function h that will get the y that maximizes the probability that f on this input is equal to y. Let's notice that h is k-junta because it only addresses the j coordinates in x, and the cardinality of j is smaller than k, so hx is k-junta. We'll now use this. In the last slide, we have seen that h is a k-junta, and we have defined f to be epsilon far from being a k-junta. So we have that the probability that they differ on some x is bigger than epsilon. Then, recalling the proof of proposition 2.9, we have seen that this expression is equal to this expression. Recall that we have seen that this inner product equals the indicator of the event that f of x equals h of x. So now we have this expression. Let's take the expectation on x and separate it into two distinct expectations over x and over z, where we sample f on these hybrid inputs. This transition is valid because our probability space is a product probability space, so we have independence in the different coordinates, so we can separate the different coordinates. And let's recall that h only depends on the j coordinates, so we have that h over this hypered input actually just equals h of x because we only sample the j coordinates from x. So we have here h of x. So we can take the expectation like in the proof of proposition 2.9 and push it because of the linearity of expectation and linearity in the first element of inner product into the inner product. And here we just push the expectation. So now we have this expression. So from the last slide, we have this expression. And now let's observe that this expectation is equal from the definition of expectation to this sum, because f is pure valued, so we can just take pure values and take each value, multiply it by the probability that we get it as an output from the function. And this is very nice because this is a formal linear combination that actually tells us for each y what is the probability that f will give it to us as an output. So now we can use this nice equation and see that the L1 norm of this formal linear combination is 1 because the L1 norm will just be the sum of all the coefficients of the formal linear combination. But in this case, those are just probabilities, so of course their sum will be 1. And on the other hand, if we take the L infinity norm of this formal linear combination, so we will get the maximal coefficient, which in this case is the maximal probability that we will get some y for some constant y, the maximal probability that we will get it. And on the other hand, this inner product, it's between h of x, which is the pure value function that we defined earlier, which will give us 1 multiplied by the y that is the most probable y that we can get from the function. And of course, because it's the only coefficient that is 1, then the inner product here will give us the probability. From here we'll get multiplied by y the probability that we get y, which is the maximal probability for some y that this y is outputted by the function, multiplied by 1 that we'll get from h of x, which is pure valued. So overall, here also we will get the maximal probability of some y that this y will be outputted by the function. So these two expressions are also one and the same. So we can just take this inner product and replace it with this L infinity norm, which is actually just like the inner product, multiplied by this L1 norm, which is actually just 1. So this whole expression equals this whole expression. Okay, so from the last slide to here, we've used a special case of Holder's inequality because taking the L2 norm squared is surely smaller than taking the L1 norm multiplied by the L infinity norm. This is just a special case of Holder's inequality, which is very famous. So we can say that this expression is bigger than the expression we had in the last slide. Then we can take the F-Einstein decomposition of f. This is just taking the F-Einstein decomposition. Then we have the L2 norm. We can take it inside the sum because this decomposition is orthogonal, so we can take the L2 norm inside the summation, like in the Pythagorean theorem or Parseval's identity. And now we can take the summation outside of the expectation because of linearity of expectation. Okay, so this expression is the same as before, but f as x is constant or a constant function, so there is no need to use the L2 norm squared of functions. We can just use the inner products between formal linear combinations. So I just replaced the L2 norm with the inner product. And now this expectation on this inner product is just equal to the L2 norm squared of fs by definition. And f is pure valued, so by Parseval's theorem, this sum is equal to 1. So we've just switched this up. And now again, we have all subsets of coordinates minus all subsets of coordinates completely contained in J. So what we've got left are all the subsets that have some intersection outside of J that are not completely contained in J. So that's the subset we have here, and that is the sum we have left. And now by proposition 2.9 that we proved earlier, this sum is equal exactly to this influence of this set which appears here. And what we've showed is that this influence is bigger than epsilon, so that finishes the proof of proposition 2.3. Now that we have finished with the preliminaries, we can start displaying the main contribution of this paper. We'll start with the main algorithm. So an important observation, and a simple one, is that for two inputs, if f disagrees on these two inputs, at least one of the disagreed coordinates are relevant. Let's assume for the contrary that all the relevant coordinates are agreed. That means that f of x, the relevant coordinates of x will get the same value as the relevant coordinates of y because they are agreed upon. So f should agree on those two inputs, but that is not the case. So that means that at least one of the disagreed coordinates are relevant. Okay. Another important observation is that we can efficiently find this relevant coordinate. We can actually do binary search to find it in logarithmic number of queries. Let's say the disagreed coordinates are s. We can compute the disagreed set without querying the function. Then we can take this set and half its size. We can take a subset D that is contained in S and will have half the size of S. And then we can take X, the input X, and change it so that it will agree with Y on the inputs D. This will actually be a hybrid input. Now, this input, it disagrees with X on the coordinates D, but it also now if before this hybrid input, X was disagreeing with Y on S inputs, now that it agrees with Y on D inputs, so the number of disagreed coordinates with Y will also be half what it was before. So this hybrid input does successfully have only half of the number of disagreed coordinates that X and Y had before. But now this F, it has two options. It can either be not equal to f of x, or not equal to f of y, because f of x is not equal to f of y, so this value must be not equal to at least one of them. But if it is not equal to one of them, and we have successfully taken down the number of disagreed coordinates by half, then that means that now we have two new inputs, one of x and y, and x d bar y d, such that the function disagrees on them, and the disagreed coordinates are now half what they have been before. So we can now go on with this process iteratively, each time taking the number of disagreed coordinates and halving it, and at the end we would remain, after a log number of iterations, in each iteration we have only one query to the function, we will remain with one relevant coordinate. Now, this binary search will also generalize to partitions. If we will take the coordinates and partition them into sets, then we can also find a partition that contains a disagreed coordinate. It is a very simple generalization. And then, because we are working on partitions on sets of coordinates and not on the coordinates themselves, so the number of queries will be O of log s, not O of log n, in the binary search. Okay, so we will now see the algorithm. The algorithm name is Junta test. It gets the function. It decides if the function is a k-junta or if it is epsilon far from being a k-junta. It will get additional parameters, s, the number of sets we will partition the coordinates of the function into, and the number of rounds of the algorithm. the values that these two parameters get are two values that will work well in the proof of the algorithm. In step 1, we will randomly partition the coordinates of all the function's coordinates. We have n variables into S sets. The random partition will be done uniformly and independently for each coordinate. In step 2, we have initializations. In step 3, we will run for R rounds, and in each round, we will first generate a pair, sample a pair from the random probability space, from the random distribution. Then we will check if f disagrees on x and the hybrid input of y written at the s coordinates and x written at the s bar coordinates. And if these values are indeed not equal, then according to the previous observation, we can use binary search in O of log s queries to find a set ij that contains a relevant variable. So after finding a set containing a relevant coordinate, we will remove all the coordinates of the set from S. So in the next iterations, when we try to find a part with relevant coordinate, we will find another parts. Then we will increment our counter that we initially set to 0. And then if this counter passed k, that means that we found at least k plus 1 parts with relevant coordinates, which means we have k plus 1 relevant coordinates. And then we will reject the function because it is not a k-junta. And if we haven't found k plus 1 parts, we will accept the function as if it is a k-junta. Now we'll see and prove the main theorem of the paper that justifies the correctness of the algorithm. It states that the number of queries required to epsilon test k-juntas is bounded from above by O k over epsilon plus k log k queries. That is the number of queries that the previous algorithm will make to the function. I'll just note that epsilon testing k-juntas means we need to accept k-juntas and reject functions that are epsilon far from being k-juntas. And of course, this algorithm is probabilistic. Furthermore, this result holds for testing functions that have arbitrary finite product domains and arbitrary finite ranges. And it also holds under any product distribution over the domain. We haven't seen and will not see any constraints that we will put on the function. And so this holds for arbitrary functions that can be very general. We'll now prove the main theorem. So let's begin by analyzing the query complexity of the algorithm. On line 3.2, we have two query accesses. One time we access f of x and one time we access f on the hybrid input. So two accesses on each time we reach this line. And we reach it at most r times because we reach it once each round. So by selection, so the maximum number of queries we have on this line is 2 times r. By our selection of r, this is 24 times k plus 1. On line 3.2.1, we reach it at most k plus 1 times because each time we reach it, that means we found a part containing a relevant coordinate. And once we find k plus 1 parts with relevant coordinates, the algorithm will reject. So that's the maximum number of times we can even reach this line. And each time we reach it, we make log s queries to the function during the binary search in order to find a part containing a relevant coordinate. So the total number of queries on line 3.2.1 is at most k plus 1 multiplied by log s. And by our selection of k and s, this is again big O of k log of k over epsilon. And so totally the number of queries is O of k over epsilon plus k log k. This is the total number of queries the algorithm makes to the function. We will now prove the completeness of the algorithm. So if f is a k-junta, it contains at most k parts with relevant coordinates. Let's assume for the contrary it had k plus 1 parts with relevant coordinates. Those parts are disjoint, so that would mean we have k plus 1 relevant coordinates, contradicting that this function is a k-junta. So really, we have at most k parts with relevant coordinates. But in this case, the function can't be rejected because the algorithm only counts parts with relevant coordinates, and only if it finds k+1 parts with relevant coordinates, it rejects. So the function won't be rejected, which means it will be accepted because we have no other option. So we have completeness, and it wasn't even conditioned on something. So this means that we have no error in the side of the completeness. The algorithm has one-sided error. If the function is k-junta, it will always be accepted. There is no probability here. We will now analyze the soundness of the algorithm. Assume that f is epsilon far from being a k-junta. By the main lemma, which we will prove later, it means that with probability at least 5/6 over the random partition, f is also epsilon over 2 far from being a k-part junta. That means that if we take S that initially contains all the coordinates, while we are yet to remove k plus parts from it, if we will not remove at least k plus 1 parts from it, then the probability that this event happens is at least epsilon over 2. That is just from the definition of being a k-part junta. While we are not removing at least k plus 1 parts from S, then this event will happen with probability at least epsilon over 2. But let's notice that while the algorithm runs, we will not remove k plus 1 parts from S, because we will remove k plus 1 parts from S only once we have identified k plus 1 parts with relevant coordinates. But in this case, we will reject the function. So every time we will reach line through dot 2 and check this event, this probability will be at least epsilon over 2 because we have not yet removed k plus 1 parts from S. So every time we reach line 3.2, we have this equation. Now, let's think about the number of times, number of rounds. We need to identify one part with relevant variable. If every round we reach line 3.2, we have at least this probability to find a relevant variable. Then that means this is a geometric random variable, and after 2/epsilon rounds at expectation, we will find a relevant variable. And if we want to identify k plus 1 parts with relevant variables, then the expectation of finding this number of parts, k plus 1 parts, it will happen after 2 multiplied by k plus 1/epsilon number of rounds, because we can just find the first part and then find the second part, and each part on itself, the expectation will be 2/epsilon, because this is a geometric random variable. And then we can bound the probability that the number of rounds to identify k plus 1 parts is at least 12 k plus 1/epsilon. This is 6 times the number 6 times more than the upper bound for the expectation. So by Markov inequality, this probability must be lower than 1/6. So now we have this equation that we know that the number of rounds cannot be too big because of Markov inequality. Let's now bound the probability that the algorithm will accept, even though f is epsilon far from being a k-junta. So the probability that it will accept is the probability that it will accept and f is epsilon over 2 far from being a k-part junta, plus the probability that it will accept and f is not epsilon over 2 far from being a k-part junta. This is just dividing this event to two disjoint events that together make up this event. And now we can upper bound this probability with the probability that just f isn't epsilon over 2 far from being a k-part junta without requiring that the algorithm accepts. Now by the main lemma, because f is epsilon over 2, because f is epsilon far from being a k-junta, then the probability that it is not epsilon over 2 far from being a k-part junta, it will be smaller than 1/6. That is the lemma. And because of the previous slide where we used Markov's inequality, this probability will also be smaller than 1/6. So overall, the probability that the algorithm will accept and it will do wrong is smaller than 1/3, which is good because this is a constant soundness error smaller than 1/2, and the algorithm is a valid Junta tester. We will now see and prove the main lemma. So let I be a random partition of all the coordinates with S parts, where this number is just an arbitrary number that will work well in the proof, where the partition is obtained by uniformly and independently assigning each coordinate to a part. So with probability at least 5/6 over the random partitions, a function f that is epsilon far from being a k-junta is also epsilon/2 far from being a k-part junta with respect to the random partition. So to prove this lemma, we will take a set J that is formed by taking the union of k parts in a random partition of the coordinates, and because it is only formed by taking the union of k parts and not k plus 1, so its influence, which is tightly related to this sum that we will observe, should not be too big, because if it's only the union of k parts, so we want to show that the function is far from being a k-part junta, then we want this sum that is related to the influence of the k parts to not be too great. So we will analyze J, we will partition it to some sets, and show that this sum is not too great, and that will be the idea of the lemma. So let's begin by looking at several cases and partitioning J. We'll begin with the first proposition. It is named high order coefficients. So let f be a pure valued function, let s be a big enough number, and let I be a random partition of all the coordinates. Then, with probability at least 17/18 over the random partitions, the high level influence of f, contained in sets that are k covered by I, meaning sets that have k parts of I covering all of them, is small. Their influence is small, meaning this sum will be smaller than epsilon/4, where the sets S that are to be considered here are sets that have k parts of I cover all of them. And also we want high level influence, so we want their cardinality to be at least 2 times k. And we want their influence to be at most epsilon/4. That is what we will now prove. We'll now prove this proposition. We'll begin by taking a set S, a subset of the coordinates, such that its cardinality is at least 2k plus 1, and we are going to bound the probability that it is k covered by the partition. We'll use a combinatorial argument, so if it is k covered by the partition, we need to choose k out of all the S parts that will cover S, so we will choose k of those parts that will cover S, and then we need to send all the coordinates of S. There are 2k plus 1 coordinates from S. We need to send all of them into those k parts, but coordinates are sent to parts uniformly and independently of other coordinates. So for each coordinate, the probability that it will get into the k parts is k/s, and we will raise it to the power because of independence. So totally we get this expression. Now this binomial coefficient, we can upper bound it with this expression. This is a famous inequality. And now we can take this k and this k and this s and this s and cancel out and get this expression. And now we can upper bound it by multiplying by e one more time and then getting this expression. Now by our selection of s is bigger than e over k. So if we remove the power, this expression will only get larger. And now again, by our selection of s, we know that this expression is smaller than epsilon/72. And now we can continue. So we will now bound this expectation. So here we have this sum where we only consider sets that are k covered by I and have a big cardinality. So we can instead sum only on sets with big cardinality and ensure we don't have any false elements here by multiplying by the indicator that the set is indeed k covered by I, so we don't get elements here that we didn't have here. And now, because this expectation is on the random partition I and linearity of expectation, we can push this expectation onto the indicator. and then expectation of the indicator is just like the probability that the event will happen, so we get this expression. And now this probability, we have bounded it from above by epsilon over 72, and we can take it out of the summation, and then we only have left this sum. But f is a pure valued function, so because of Parseval identity, this sum is smaller than 1. So overall, this total expression will be smaller than epsilon over 72, so this expectation is smaller than epsilon over 72. So by Markov inequality, the probability that this sum will be smaller by epsilon over 4, which is much bigger than this, is at least 17 over 18, as required from the proposition. So now we will go on to the next one. Now we'll prove the proposition named coordinates with large low order influence. So we'll first define the set of coordinates with large low order influence. So for pure valued f, we'll define HLF to be the set of coordinates such that their low order influence is large. And now we will prove that with high probability, a random partition of the coordinates completely separates this set. So let f be a pure valued function, let theta be bigger than 0, and let s be big enough. Then with probability at least 17 over 18, a random partition satisfies the condition that for all its parts, each part will share at most one element with HF, meaning that the random partition completely separates HF. We will now prove this proposition. So by corollary 2.13 that we've seen before, we can immediately see that the cardinality of HF is smaller or equal to 2k over theta. Now, let's bound the probability that there exists some part that contains at least two elements from HF. This is the complementary event that each part shares at most one element with HF. So the probability this event will happen if two elements from HF will be sent to one part from one of S parts, and we don't care which two elements of HF, we don't care what part from S parts, so this is again a combinatorial argument. And for the both of them to be sent to the same part, we need to, again, they are sampled uniformly and independently, so we can just use this probability. And now because the size of HF is at most 2k over theta, we can upper bound this binomial coefficient trivially with this expression. S over S is just S, so this and this cancel out, and we've got 1 over S. And let's take the 2 out, we have 4, let's put in S the value we have set in the proposition, so we've got this, and this is just equal to 1 over 13. So if the probability that the complementary event is smaller than 1 over 18, then the probability that HF that the partition completely separates HF is at least 17 over 18, like we wanted from the proposition. So now we will go on to the next and final proposition. Now we will see the final proposition named coordinates with small low order influence. So let f be a pure valued function, let s be big enough and theta be small enough, and let I be a random partition of the coordinates. Then with probability at least 17 over 18, the low order influence of this set that relies on the ith part is at most epsilon over 4k, and this inequality should hold for every part. We will now prove this proposition. So let's fix some part I and define for all coordinates j, xj to be the low order influence of j if j is in this set. Otherwise, let's fix it to 0. Now we can upper bound the influence of this set by summing the influences of the individual coordinates from this set. So this inequality holds because influence upholds subadditivity, as we've seen in a previous corollary. And now this sum of xj's is equal to this sum of influences because xj is equal to the influence when the index is taken from this set. So we can just take all indexes, and then on indexes from this set there will be equality. For other indexes this will be 0. So all in all, it's the same element assigned here and here. Now, another important thing we want to notice is that xj's are independent with respect to the random partition, because their values are either this value which is not dependent on I, or this value which is not dependent on I. The only thing that depends on I here is if j is in the I part of the partition or not. But j is some coordinate, and it is chosen independently of other coordinates. So xj will get this value or this value independently of other xj's, because coordinates are taken independently. Now, by proposition 2.12 that we've seen earlier, this sum will be smaller or equal to 2k. Now, for every coordinate, the probability that it will be sent to the part I is 1 over s, because coordinates are sent uniformly to the parts. Now we can take this expectation and push the expectation in, because of linearity of expectation, into the sum. And xj is a kind of an indicator, because it gets 0 on one event and otherwise it gets some other value, even though this value is not exactly 1. So we'll get something very similar to indicators. Instead of just getting the sum of probabilities, we'll get the sum of probabilities multiplied by the value, which is not 1 here because it's not exactly an indicator, it's similar. And we will just sum here for relevant indexes, because if j is in HF, so xj gets 0 for sure. So we will avoid j's that are in HF, and we'll get this sum. So this probability equals 1 over s, and this sum is at most 2k. So all this expression is bounded from above by 2k over s, and in the proposition we chose s is bigger than this expression, so just by changing the sides of the expressions we get this inequality, which we'll now use. Like I've mentioned in the previous slide, epsilon over 8k is bigger than the expectation of this sum of xj's. So now we will use Hovding inequality to bound this probability that this sum of xj's is bigger than the expectation plus t. We will bound it with the value. So why can we use this inequality? Because xj's are independent, as I've mentioned earlier, and they are bound between 0 and this value without the square, because the two values they can get is either 0 or this value. So this is a Hovding inequality. And now let's look at the denominator. So this is the denominator, it's sum of squares. So we can actually put an upper bound on it by taking out the maximal element out of the sum. And now this is the maximal influence on some coordinate, which is not of high influence because it's not in HF. It's a low order influence, but it must be small because it's not from the set of high low order influences. So this influence is at most theta. On the other hand, this sum of influences we have shown in a proposition 2.12 that it's at most 2k. So here we have that this is at most 2k theta. So now we can put an upper bound on this whole expression by switching this up with 2k theta, and 2 and 2 cancel out, and we got this. Previously, we've seen that this influence is smaller than this sum of xj's. So if this influence is bigger than this value, this sum of xj's will also be bigger than this value. This and these are the same values, it's just represented as an addition. So this event, if this event is true, this event is also true. So of course this probability is smaller than this probability. Now here we can again use Hovding inequality and put in the values of s and theta that we chose in the proposition and get this inequality. And now k and epsilon cancel out, and we've just got e to the minus of log 18s, which is 1 over 18s. But now remember that this whole analysis was for a fixed part I. So you can use union bound to say that the probability that even for one part this influence is bigger than epsilon over 4k is at most over 1 over 18, but this means that with probability at least 17 over 18, all parts uphold that their influence is smaller or equal to epsilon over 4k, which is what was demanded from the proposition. Now that we have finished proving all the propositions, let's read again the lemma to remember it. So let I be a random partition of coordinates with S parts obtained by uniformly and independently assigning each coordinate to a part, with probability at least 5 over 6 over the random partitions. A function f that is epsilon far for being a k-junta is also epsilon over 2 far for being a k-part junta with respect to the random partition. So now let's prove this lemma. We'll now prove. So let J be the union of any k parts in the partition. The influence of all the coordinates but the coordinates in J is equal, according to proposition 2.9, to this sum minus this sum. Now let's set theta to be this value and set S to be this value from the Junta test algorithm. So here I've put the conditions for the 3 propositions that we have seen, and if you want you can do the numbers game and see that theta and S really uphold these conditions. Therefore we can use these 3 propositions and now prove the lemma. Now we will partition the subsets of J into 3 sets, H, L, and B. In H and L we will have small subsets. In H we will have subsets contained in this set, and in L we will have subsets not contained in this set. And in B we will have big subsets, and it's easy to see that the three of them form a partition of the subsets of J. So this influence that we have seen that is equal to this expression, we can take this sum of S that are subsets of J and instead split it into these 3 sums where we use this partition of J. And now, because every S that is in H is also contained in J intersection with HF, we can make this sum even bigger by taking all S that are contained in J intersection with HF, but then this expression minus this expression will just be equal to this influence. So let's just say that this is a lower bound to this expression. So now we have this expression. Now we will use the 3 propositions we have seen to bound the different parts of the sum we have seen earlier. So by proposition 4.3, with probability at least 17 over 18, every part in the partition has at most one common element with HF, but J is a union of k parts, so J has at most k common elements with HF. Because it is the union of k parts and each part has at most one common element with HF, then J has at most k common element with HF. Now, because the size of this set is at most k, and F is epsilon far for being a k-junta, we can use proposition 2.3 that we have proven earlier. And it implies that the influence, this influence that is one of the elements in the sum of the previous slide is bigger than epsilon. Now, by proposition 4.4, with probability at least 17 over 18, for every part J, this inequality holds. So now we can take this sum and just put in the definition of L. So we will consider sets S that have a constrained cardinality and that are completely contained in J but are not completely contained in HF. So let's observe that those sets, they have some element which is not in HF, but it is in J because they are contained in J. So they must have some intersection with J minus HF. So this sum must be bigger than this sum. Now this sum, according to proposition 2.9, is equal exactly to this sum. Now here we have J, which is the union of k parts, but according to proposition 4.4, this influence, if we look at parts, not at J, is at most epsilon over 4k. But by subadditivity, we can say that this influence is at most k by epsilon over 4k, which is the influence that that corresponds to one part, because J is a union of K parts. So this influence is at most K multiplied by epsilon over 4K, and this is equals epsilon over 4. So now we have also bounded this element. And finally, the set beta was defined as sets that have big cardinality, but they are also contained in J, which is the union of K parts, meaning that these sets are K covered by the partition. So we can just say that beta is contained in the set of all subsets of all coordinates that have big cardinality but are K covered, because the original beta was K covered by J, which is the union of K parts. So now, by proposition 4.2, with probability at least 17 over 18, this sum at the worst will be, at the worst case, this sum, because beta is contained in this set of all S that are K covered by I, and S has large cardinality. But by proposition 4.2, this sum is at most epsilon over 4 with high probability. So now we have also bounded this sum. So now let's finish the proof. Combining the previous results, we obtain that the influence is bigger than this expression, but we've bounded each of these individual elements by these numbers. So overall, the influence is bigger than epsilon over 2, and that happens with probability 5 over 6, like we like the lemma requested, because from union bound, the probability that one of the bounds doesn't hold is 3 over 18. So all bounds hold with the complementary probability, which is 5 over 6, just like we wanted. So to summarize, testing whether a given function is a K-Junta is useful for different scientific purposes. It might make our life easier when solving optimization problems and help with overfitting, etc. The paper presented a new K-Junta tester algorithm that makes only a very small number of queries to the function, which is asymptotically optimal up to a logarithmic factor. This algorithm has one-sided error as well. And the idea of the algorithm was to group coordinates together, to partition the coordinates, instead of handling them individually. And the proof of its correctness heavily relied on F-Einstein decomposition, which is an extension of the Fourier decomposition. Thanks for listening. Bye.